Okay, hi guys. In this video, I'm going to go over the equation sheet for, we're going to do one video on mechanics, one video on electricity and magnetism, and we're going to focus on how this works for this year's exam, the 2020 exam. So let's just start at the beginning. What we're going to do is we're going to look at some equations, and then let's just think about some situations where you see them, okay? And let's also try to put these equations into words and make sure that we cover the range of validity, right? So not all of these equations are good for every single situation. So we want to make sure that we have a range of validity that we consider for each one. Okay, so let's just start with these first three. The most important part of using these three, which of course are the kinematic equations, is what is the range of validity for this one. And that is that the acceleration has to be constant, okay? And because we know Newton's second law right here, we know if the acceleration is constant, that means the net force is constant. So you cannot use these in situations where the acceleration is changing, which means that you have a time variant net force. In rotational motion, of course, you have your counterparts to this, and they very often like to ask questions about things rotating and the torque is changing, right? So maybe something's falling. If the torque is changing, then the angular acceleration is changing, which means you cannot use these. And in general, if you can't use these, energy conservation is going to be probably your next best bet there. Okay, let's just put this into words, okay? This is the velocity of an object that starts with this velocity, has this acceleration, and is accelerating for that amount of time, right, is given by this equation. So that's the velocity. Very, very important to look at the components here. When you think about projectile motion, we use these equations in sort of two dimensions, right? In the x dimension, in the horizontal component, acceleration 0. So this is an equation that is, trivial, that says if there's no acceleration, the velocity stays constant. So we know that. This one gives you the same thing. This one is useful for the x direction. This term goes away, but this is really just, the definition of displacement that you learned, when you were in 8th grade, that distance equals speed times time, right? And that's only true for a constant velocity, which it is, or constant velocity, or you can do some hand waving, and that can also be average velocity. So, that's good for in the x direction for projectile motion. For y, this is our, g down, right, is our a sub y for projectile motion. And so you can get the time to get to the top by saying, oh, at the top, right, it's only moving in the x direction. There's no y component of velocity. And so the time is just whatever, right? Usually you have some v sub naught y, right? And so you can figure out the time is that v sub naught y divided by g. So there's some obviously like cute tricks when you do use these for projectile motion. So, okay, that's probably enough on the kinematic equations. This, of course, is Newton's second law. This is true always, but if the net force is constant, then you get that nice constant acceleration, which means you can do these things. But in general, this is just true. We can also write Newton's second law. This is actually how Newton wrote it. Was dp dt. P here is momentum, of course, which is right here, which is mass times velocity. So you can think about things in terms of Newton's second law here, or if you're dealing with momentum, then sometimes that's the more natural way to think about it. Anytime you see an integral, right, you know that if you have an f versus t curve, right, that underneath is that integral. That is the impulse. That is m delta v, right? So that's where we get the different situations of force versus time, where we have a short amount of time and therefore a large average force, or if you have a greater amount of time, you have less of a force. Okay, I'm going to pause right now.